All right, welcome. Today, we're diving into a really challenging four-mark geometry proof from a GCSE higher tier paper. We're not just going to solve it. We're going to break down how to think like an examiner so you can guarantee you get every single mark. So here it is, question 21. You've got a circle snuggled between two regular hexagons, and you're asked to prove this inequality with pi in it. Now, you know, the tricky thing about these show that questions is you're already given the answer. The real test is showing a crystal clear logical path to get there. Exactly. It's not about finding the answer, it's about building a perfect, flawless argument. So the big question is, how do you make sure you're ticking every single box the examiner has on their list? Well, here's the secret weapon, the official mark scheme. This thing tells you exactly what gets you the marks. We're going to use it as our guide to build our proof, step by step, to make sure we hit all the requirements. Okay, so here's our game plan. We'll start by understanding the setup, then we'll find the perimeter of each hexagon, build the key inequality, and finally wrap up the proof to lock in all 4 marks. All right, first things first, let's really get our heads around what we're looking at here. We have a circle with a radius we'll call r. There's a smaller hexagon inside with its corners just touching the circle, and a bigger one on the outside with its sides just grazing the circle. Our job is to connect their perimeters to prove something about pi. So let's just think about this logically for a second. The distance around the circle, its circumference, has to be more than the perimeter of the small hexagon, but less than the perimeter of the big one, right? It just makes sense. That's the core idea we're about to prove with numbers. First up, let's tackle that smaller inner hexagon. Our mission here is to find its perimeter in terms of r. Getting this right will bag us our very first process mark, a P1. And look what the mark scheme says, it's super specific. We get that first mark for a process to find the length of half a side or the perimeter. You could use trigonometry here, but honestly, there's a much slicker way to do it. If you look at a regular hexagon drawn inside a circle, you can actually split it up into 6 identical equilateral triangles. Think about it. The 2 sides of each triangle coming from the center, those are both the radius, r. And the angle at the center is 360 degrees split 6 ways, which is 60 degrees. So if 2 sides are equal and the angle between them is 60, all the angles must be 60. And because they're equilateral triangles, that third side, which is the side of our hexagon, it has to be r as well. So the total perimeter is just 6 times r. Simple as that. By showing that, boom, our first process mark is in the bag. Okay, 1 mark down, 3 to go. Now let's look at the outer hexagon. This one needs a little bit of right-angled trig, but don't worry, the mark scheme points us right where we need to go. Yep, for our second process mark, we need a correct method to find the perimeter of the larger hexagon. The scheme pretty much nudges us towards using trig, so let's see how that plays out. Okay, so how do we tackle this? If we draw a few lines from the center, we can create 12 identical little right-angled triangles. The angle at the center of each of those is just 360 divided by 12, which is 30 degrees. Now, in this little triangle, the radius r is the side right next to that 30-degree angle, the adjacent side. And the side we need to find, which is half of one of the hexagon sides, is opposite that angle. Let's walk through this. We're using SOHKAT, right? We have the opposite and adjacent sides, so that's tan. Tan of 30 degrees equals half a side, divided by r. A bit of rearranging means a full side is 2 times r times tan 30. Now the exact value of tan 30 is 1 over the square root of 3, so one side is 2r over root 3. The full perimeter is 6 times that, which gives us 12r over the square root of 3. And to tidy that up, we rationalize the denominator, which gets us to 4 root 3 times r. And just like that, we've nailed our second mark. All right, check this out. We've got all 3 key pieces now. We have the inner perimeter, 6r, we have the outer perimeter, 4 root 3r, and we know the circle's circumference is 2 pi r. It's time to put them all together. And what does the mark scheme say? It confirms it. The third process mark is literally just for writing down the correct inequality. We're just putting on paper what we figured out earlier, that the circle is trapped between the 2 hexagons. This table just lays it all out for us. It's the mathematical way of saying the shortest path is the inner hexagon, the longest is the outer, and the smooth curve of the circle is somewhere in between. So let's just write it out. 6r is less than 2 pi r, which is less than 4 root 3r. By putting this down, based on all our correct work so far, we've just pocketed that third mark. See? Not so bad. Okay, we are in the home stretch now. Seriously, the hard part is over. All that's left is a little bit of algebra to clean this up and make it look exactly like the answer in the question. And this last mark is what's called a C1, a communication mark. It's not for some new tricky calculation. It's for showing you can finish the argument clearly and accurately without making any mistakes. It's all about that final, clean presentation. And the algebra couldn't be simpler. You see how every part of our inequality has a 2r in it? Well, since r is a radius, we know it's a positive number. That means we can just divide everything by 2r, and we don't have to worry about flipping any of the inequality signs. And what does that leave us with? Well, 6r divided by 2r is 3, 2 pi r divided by 2r is just pi, and 4 root 3r divided by 2r gives us 2 root 3. And there it is. We have shown, through clear, logical steps that line up perfectly with the mark scheme, exactly what the question asked for. That is a full 4 marks. So, what's the big takeaway here? It's the method. By using the mark scheme as a blueprint, we turned a really tough-looking proof into a checklist of small, manageable steps. So the challenge for you now is, how can you use this exact same thinking on the next tricky problem you come across?